So, dear colleagues, good afternoon. It's my great pleasure to start our today's seminar and to introduce our today's speaker, Jacek Dziarmaga from Jagiellonian University in Krakow. His talk is titled 2D Tensor Networks for Quantum Simulation. And not only the name of the city is very similar. Krakow sounds quite close to Kharkiv, but also
Kharkiv, right?
It depends. Kharkiv in Ukrainian, or previously it was mostly known as Kharkov. But also here we see on the top of your picture, we see the colors of our flag. With one slide, I would like to introduce our today's speaker with brief biography. Most of the biography is related to Jagiellonian University, so this abbreviation appears for this reason. Interestingly, master degree and PhD degree were defended very close, with a difference of 1 year. Then habilitation, which is close to our Doctor of Science degree, was gained as the professorship there. Besides the career in Jagiellonian University, Professor Dziarmaga was also in Durham University and in Los Alamos National Laboratory. Now he is also a divisional associate editor of Physical Letters, and also he delivers lectures and supervises students. 7 of them defended PhD degree, and as we discussed before the seminar, most of them returned and stayed in science. What else? What else? Today we have the Independence Day of Poland. Jacek, greetings, and the floor is yours.
Yeah, thank you. Thank you. Very nice introduction. And it's a pleasure to give this talk on our Independence Day for people who are fighting for their independence. So I will thank you for invitation, first of all, and for the introduction. It's a full screen. Yes. So I'm going to talk about two-dimensional tensor networks. This is what we are doing because we think that 1D tensor networks are for intelligent people and 2D tensor networks are those. And you need to be intelligent from time to time as well, but you need a character. Yeah, and here I will try to I try to arrange this talk in such a way that we work in parallel to quantum simulations, whatever it means. Okay, so here I list some of my collaborators. The first 2 rows are people from Jagiellonian University. Ori Tru is now in Dresden, in Max Planck Institute. And the bottom line are people, Mohammad Amin, that you mentioned, people from D-Wave and friends. These are our incidental collaborators. But, well, we did work with high impact, apparently. So the outline, so I was invited to be pedagogical, so I tried. So first of all, I will make a tensor network primer. Introduction to tensor networks, Kibble-Zurek mechanism, because that's our quantum version of Kibble-Zurek mechanism. And then 2 topics, computational advantage in D-Wave quantum annealer. This is this science paper with D-Wave people. And the second topic is thermal states in 2D. And the example is the Fermi-Hubbard model and TJ model. That is a strong coupling limit of the Fermi-Hubbard model. These are the 3 main papers. although I will mention more. The second is about Hubbard model, and the last one, print, is about the TJ model. And at the bottom, you can see the main character of this talk. It's a two-dimensional tensor network that is called IPEPs. IPEPs mean I means infinite, PEPs means per entangled projected state, but nobody is using the full name. It's kind of historical. One could call it a tensor product state. It's made out of tensors. So in order to understand this diagram, I will make a brief introduction into tensor networks. I will start from a basic dictionary. So as you could see, tensor network is made out of such geometrical shapes, and every geometrical shape here is a tensor, and every line is a tensor index, right? So a shape is a tensor. So for instance, a number, a scalar, has no indices, so it's just a shape. A vector has one index, one line sticking out, open line sticking from a shape. Matrix has two indices. We can consider also rank 5 tensors. This wave function ansatz was made out of such tensors. So these are the basic elements, the tensors. And then we can make tensor contractions. So for instance, when you see such a diagram, the open lines are open indices, but there is one line connecting the two tensors. And a line connecting two tensors implies that there is a contraction, that there is a summation over this index. So these open indices have some definite values, but this line connecting two tensors implies, it's like Einstein summation formula, summation convention. A connecting line means a sum, a contraction. So for instance, here we have two matrices, two rank 2 tensors. This is matrix number 1, matrix number 2, and they are connected by one line. And this connection means matrix multiplication, a contraction through this common index. And the outcome, the net outcome of this contraction is an object that could be replaced by a single shape with two open lines. An object with two open lines is another matrix, and this matrix is a product of these two matrices. So this is how to read this diagrams. Okay, now let me apply this dictionary to a quantum state. So we consider quantum lattice models. Hilbert space is a product of Hilbert spaces, for instance, spins 1/2. And here is a pure state on an infinite square lattice. I will talk about square lattices. So we can write it like this. Here is a basis state. It's a product basis. Every j is for spin 1/2. It's either up or down, or whichever basis you prefer. And we have a sum over these j's. The number of these indices is the same as the number of lattice sides. And that means that, well, if you look at this psi with indices as a tensor, then the total size of this tensor grows exponentially with system size. And this is why many people say that we need quantum computers, okay? But there are some crazy people who believe that at least some problems, and some of them very important problems, can be solved with tensor networks. So the main idea of tensor networks, the way they work, is to divide and conquer. This huge exponentially large tensor is divided into smaller tensors, into a contraction of smaller tensors. Here we have one tensor at every lattice side. The red indices pointing down are the j indices. They are the physical indices. The red indices are the physical indices. But in addition to physical indices, we have these black bond indices connecting nearest neighbor tensors. They are virtual indices. They have nothing to do with a, or at least not literally, with a physical Hilbert space. And their dimension is a parameter. So here we have a contraction through a bond index, and a bond dimension, the dimension of this index, the size of this index is d. So, for instance, if we set a special case, not very interesting, but it's a simple special case is when d is equal to 1, then in fact we don't have any contraction between nearest neighbor tensors, and when this wave function is a product of wave functions at different lattice sites. So then this variational ansatz becomes a one-side mean field ansatz, right? But as we increase d, we introduce correlations between different sites in a systematic way. The more d, the more entanglement between different sites or more correlations. Okay, so let me make some summary. Red indices are physical indices. This ansatz satisfies area law for entanglement entropy. If you take a subsystem, cut a part, you take part of this infinite system, you define it as a subsystem, then the entanglement between the subsystem and the rest of the infinite lattice is bounded from above by the boundary of a subsystem times a coefficient that is proportional to this d.
Sorry, black d is an integer.
D is an integer, yes. This is size of an index. Index runs from 1 to d, or from 0 to d minus 1. But that's a range of an index. So for d equal to 1, in fact, we could then neglect this index here, and then we have a product. Then every such a ball with a physical index is a vector on a single side. Now, a wave function for a single spin, for instance, and then it's a product ansatz. With increasing d, we introduce more and more correlations into this ansatz. So in this sense, d is a control parameter. Now, if we can converge our observables in increasing d, then we are quite confident that we got the, well, numerically exact result. There is no sign problem in contrast to quantum Monte Carlo. There is no sign problem because it's a variational ansatz, and what is more, in order to calculate expectation values, or say gradients, we need to calculate gradients to optimize the ansatz. We don't need to use any Monte Carlo. We don't need to do any sampling. There are efficient ways to calculate expectation values, gradients, etc., without any statistical sampling. And this ansatz proves extremely successful for ground states of strongly correlated systems like the Hubbard model, Shastri-Sunderland model, Heisenberg model, Kagome lattice, J1, J2 model. Almost every month there is some new work. Okay? And it was successful in a sense that, for instance, variational energy was much lower than obtained by different methods. Okay, so we were motivated by this success, and our main research topics are thermal states. But by thermal state, I mean a Gibbs operator. And a Gibbs operator is an exponent. Beta is inverse temperature, H is a Hamiltonian. So if you can simulate such a Gibbs state, then you can also simulate time evolution. Just make beta imaginary, and then it's a unitary time evolution. So there are some common methods, both for thermal states and for unitary evolution. For thermal states, it's bound to be more useful. And the reason for this, so let me first of all, okay, this is an oversimplification, but this Gibbs operator has matrix elements like this, and they are a tensor. It's a huge exponentially large tensor, but this tensor can be also divided into single-side tensors. Here is an example of a 4x4 lattice. The upper I indices are the top red lines, and the lower J indices are the bottom red lines. And we have this virtual bond index, this integer bond index, over which we make contraction. So again, this is this divide and conquer strategy. We divide it into smaller tensor, and then we can optimize one tensor. We can conquer one tensor at a time. Okay. Now, why this is an efficient representation for a Gibbs state? We know that Gibbs state, by definition, maximizes entropy for a given average energy. This entropy is entropy of entanglement between the system and the rest of a universe. And because entanglement is monogamic, if you are strongly entangled with the rest of the universe, then there is little entanglement left inside the system. Right? So the Gibbs state is heuristically speaking, is internally the least entangled state for a given average energy. And this is why it can be represented by a tensor network with a finite D. Okay, so these are intuitions, but they can be more precise by an area law for Gibbs states of local Hamiltonians, area law for mutual information. We have a subsystem A, the rest of the infinite lattice, and this mutual information in the subsystem and the rest of the lattice is bounded from above by a boundary, by the size of a boundary of a subsystem. Of course, the subsystem has to be sufficiently large. This is asymptotic result that's sufficiently smooth. On the other hand, for this pair-entangled projected operator, one can demonstrate that the area law between subsystem and the rest in this density matrix is bounded from above by the boundary times a coefficient that depends on this bond dimension, on the logarithm of the bond dimension. It's logarithmic because this mutual information is entropic, so it's also logarithmic in correlations. Right? So we can expect that this ansatz can provide an efficient representation. By efficient, I mean representation with relatively small d, tractable d, for thermal states. And in particular, for classical Hamiltonians, this d may turn out to be very small. For instance, for classical 2D Ising model, as was discovered by Onsager, even though he didn't use the term tensor networks. So as was shown by Onsager, this bond dimension is 2. Right? D equal to 2 is enough for exact representation for a thermal state in two-dimensional classical Ising model, even at the critical point where the correlation length diverges. Right? You can get exact representation. So apparently, D can be very small for classical correlations. You need D for quantum correlations. That's the intuition. I unfortunately I don't have a theorem to make it more precise, but that's kind of experience. That's what we learned. Later on, this idea was taken over by Baxter, by Nishino, and they were talking about tensor networks. And there is a whole branch of classical statistical physics where they use tensor networks. Okay, so again, so that was explanation why I believe it's a good representation. Now, the Gibbs operator is a time evolution, but I'm interested in quantum Hamiltonians, right? So in order to make evolution of a quantum Hamiltonian, we divide the evolution into small time steps. And then here is an example, two-dimensional quantum Ising model. It has two terms, Z is sigma Z, X is sigma X, Pauli matrices, ferromagnetic interaction, transverse field. So there are two terms in the Hamiltonian that do not commute with each other. And the small time step here can be approximated by the so-called Suzuki-Trotter decomposition. This is second order Suzuki-Trotter decomposition. And the application of this term with transverse field, this Hamiltonian Hx is local. So this exponent is a product of local exponents, one-side exponents. So in order to apply this exponent to a tensor network, you just apply an exponent to every physical index of a tensor network, and that's it. You just apply it here, and you get a new tensor after application of this network. Now, the problem is with this, we have a problem with this central exponent, with this nearest neighbor ferromagnetic interaction, or any say, two-side interactions. It's a product of nearest neighbor Ising gates, well, imaginary Ising gates. They commute with each other, so the order of gates does not matter. And here is how they are. And this is how they are applied to a tensor network. So here is the IPEPs. And I suppose I want to make such an imaginary time evolution on this IPEPs. And for instance, I apply a trotter gate to these two sides. Now I choose two sides somewhere and apply a trotter. Now this Ising trotter gate can be written in this form. It's either a product of two identities or the product of two sigma z's. So it is a sum of two products, right? So this sum can be represented by a sum over an index. And here we have one operator in this physical red indices, the left trotter operator. And here is the right trotter operator with two physical indices. And when this index is 1, then these operators are identities. This is this term. And when this index is 2, then these operators, each of them, is sigma z, or just z, with some numerical factor. Yeah. So we can always make a singular value decomposition of a trotter gate into left and right operator. And in case of this Ising gate, the rank of this decomposition is 2. Now, what we do? Next, we make contraction over this red index in order to make a new tensor that is made out of this old tensor here and the left trotter tensor, and the same on the right. We make a contraction over this red index, and a new tensor is made out of this old right PEPS tensor and the right trotter gate. Okay, so this way we get new tensors, but now the bond dimension, now between these new tensors, we have two indices, index of dimension D and another index of dimension R that is equal to 2 in our case. So the total bond dimension between these new exact tensors is 2 times D. Yeah? So we get exact tensors with bond dimension 2D. Now, the problem is that bond dimension was increased. Yeah, it seems that it's increased it's doubled in every time step. If it were doubled in every time step, then the bond dimension would grow exponentially with time or with a number of steps. Okay, and we cannot afford it because the bigger is the D, the more expensive are the computations. So this is why after every trotter gate, we have to truncate this bond dimension back to D, back to the original bond dimension. And this can be done quickly with singular value decomposition between left and right. And then we get to these two truncated tensors, purple tensors, with the original bond dimension D. Singular value decomposition is the optimal truncation in a Euclidean norm. If these two tensors had no environment, no infinite tensor environment, then singular value decomposition would be optimal truncation. Now, the problem with singular value decomposition is that it's optimal in Euclidean norm, so that means that every direction in space, in this virtual space, is equally important. Yeah? But these two tensors are embedded in this tensor environment, and this tensor environment provides a metric tensor that is non-trivial. And it turns out that some directions are more important than others. And that's why these two tensors have to be optimized in a tensor environment. We do not like to use the full infinite tensor environment because we cannot contract it exactly. We prefer to use small cluster environments. So with this cluster, we get a non-trivial metric tensor. And in this non-trivial metric tensor, we can make better use of this limited bond dimension. And of course, we could take a bigger cluster, but to make a contraction of a bigger cluster is more expensive. But with a bigger cluster, we would make even more efficient use of this limited bond dimension. So there is some kind of trade-off. So in the end, we optimize these tensors, and the cost function is a Frobenius norm of the difference between the left diagram and the right diagram. And after they are converged, after these two tensors are converged, all tensors on the lattice are replaced with these new converged tensors. So these are the basic ideas how we make time evolution. Here is an example of imaginary time evolution, but the same can be done for real time evolution when beta is, so to speak, imaginary. Okay, so now, so that was a primer on tensor networks. How about time? 20 minutes is gone. Okay.
May I ask a question, Jacek,
Yes.
on the previous procedure? You mentioned that so every application of Tortor gate you need to truncate via SVD. Is it just empirical observation, or, for example, why not to make several Tortor gates and then every third time just truncate, or more frequent, so more seldom?
More random truncations, you mean?
Yeah. Just not every step, but every second step or every third step make truncations.
Yeah, so one can optimize. We always truncate after one step, just to avoid the growth of a bond dimension. But it depends on the context. Yes, you could do it every third step, and then you save some time.
Okay.
But then after the first step, you have twice the bond dimension, then 4 times the bond dimension. So it depends what you are doing. That's sort of basic stuff. And I want to stress, we don't do SVD. SVD is just to initialize these new tensors, and then they are optimized in this tensor environment. And recently I have a paper on loopy tensor networks where I go beyond this, can be done even better, even though these new methods are not very efficient, but I hope they just may indicate a new direction that I have to elaborate on them. Okay, so quantum Kibble-Zurek mechanism. That's an introduction to this, say, supremacy claim papers. So what we are doing here, so it's okay, change of topic, another semi, right? Almost. So it's an adiabatic, we are driving a Hamiltonian slowly. We make a ramp of a quantum Hamiltonian. It's initialized, the state of a system is initialized in the ground state of initial Hamiltonian. And then the Hamiltonian is driven across a quantum phase transition. Yeah? When time is equal to 0, we are crossing a quantum phase transition. In other words, there is a parameter in the Hamiltonian, G, that has a quantum critical value, GC. So like in any textbook on renormalization group or on phase transition, we can define epsilon, that's a dimensionless distance from the critical point. Epsilon is 0 at the critical point. And as we know, at the critical point, the gap goes to 0, like epsilon to power z nu. Z is dynamical exponent, and nu is correlation length exponent. So correlation length diverges like epsilon to minus nu. And this means, at least for an infinite system, that no matter how slowly you drive the Hamiltonian across a quantum critical point, the evolution must become non-adiabatic in a neighborhood of a quantum critical point. So to speak, more mathematical, there exists a neighborhood of a critical point where the evolution must be non-adiabatic. Okay, and how to quantify it when it's adiabatic, when it's non-adiabatic? Let us consider a quench that can be linearized near the critical point. Yeah, so epsilon is a function of time, but close enough to the critical point, it can be linearized. Tau q is called quench time. It's a misnomer, but it's called this way for historical reasons. So actually, it's a ramp time. It's not a sudden quench. Now, with this linearized formula, you can calculate transition rate, time derivative of epsilon divided by epsilon. I choose this as a definition because this is relevant for adiabatic perturbation theory. And what you get is 1 over t. So here I plot transition rate that diverges like 1 over t. T equals 0 is the quantum critical point. But on the other hand, I have a gap that goes to 0 at the critical point. So when the transition rate is faster than the gap, then the evolution is non-adiabatic. And this happens between minus t hat and plus t hat. T hat is the time when gap equals the rate. Rate equals the gap at t equal to minus t hat. We can substitute these formulas, and then we get t hat that scales like a quench time to a power that is made out of critical exponents. And so in this way, we estimate this minus t hat and plus t hat. In between them, evolution is non-adiabatic. So let me repeat again to add more details. We start from the ground state, far away from the critical point. We slowly drive the Hamiltonian, and the evolution initially is adiabatic until minus t hat. So we arrive, the state of the system arrives at minus t hat following the ground state of the system. So here we still are in the ground state of the system. Then it's non-adiabatic. In first approximation, we can assume that this is impulse stage. So in other words, the state of the system does not change between minus t hat and plus t hat. It just cannot catch up with the change in Hamiltonian. And in this way, we arrive at plus t hat with a state of a system equal to the ground state of a system at minus t hat. But the ground state of a system at minus t hat is not a ground state at plus t hat because we crossed quantum phase transition. The ground state at plus t hat is qualitatively different from this old ground state. So we arrive at plus t hat with a system in an excited state. But we know, for instance, that the correlation length in this excited state is equal to the correlation length in the ground state at minus t hat. In the ground state of a Hamiltonian at minus t hat. And again, playing with these formulas, we find this formula for this Kibble-Zurek length. It's again tau q to a power, which is z is missing here. Yeah. So this correlation length grows with a quench time or ramp time, grows like a power of a ramp time. And here is an example of a quantum Ising chain that is exactly solvable. Here is a final state, or in fact, a final state. So here we make a ramp from a paramagnetic phase to a ferromagnetic phase. And this is a final state in the ferromagnetic phase, or an example. Actually, a state is a quantum superposition of states like this. But, oh, something happened.
Sorry, it was me who accidentally switched off your
Share.
Would you please share again?
Okay.
I wanted to block users from making comments on the screen.
No, but I'm also blocked.
Yes, sorry. Just a second. Yes.
Okay. So here we are. So we end in a superposition of such mosaics of ferromagnetic domains, but the typical size of this ferromagnetic domain is proportional to square root of tau q. And this is exactly solvable example. So many more things can be calculated here. Okay, we can elaborate a little bit more on these basic ideas. So again, the same picture. Here I would call it a Kibble-Zurek stage between minus t hat and plus t hat. And during this stage, we have a unique time scale for the physics during this non-adiabatic stage, and a unique length scale, psi hat, and they are not independent. T hat is proportional to psi hat to the dynamical exponent. So in fact, the only scale is psi hat. And one can formulate, say, KZ scaling hypothesis for short. So here is expectation value of an operator that depends on a distance. It sounds abstract, but for instance, it could be a two-point correlation function. Here is scaling dimension of this two-point correlation function. And the hypothesis claims that when you multiply this expectation value by psi hat to delta O, then you get a non-universal scaling function, but this scaling function depends on a scaled distance and scaled time. And that's all. Yeah? So this is a similar scaling hypothesis to the one for static critical phenomena. Okay, so this was introduction to KZ, and now some simulations of KZ. As I mentioned, 1D is exactly solvable, and to make contact with quantum simulations, this 1D Kibble-Zurek mechanism was quantum simulated with Rydberg atoms and also with coherent D-wave. The 1D quantum Ising model was simulated. So the exact, one can say that the exact solution was verified by experiment, or one can also say, put it the other way around, that the experiments or quantum simulators were verified by this exact solution. But here I want to talk about our paper with Markus Heil and Schmidt and Wojciech Żurek and Marek Rams, Science Advances 21, two-dimensional quantumizing model. Yeah? Nearest neighbor ferromagnetic coupling, transverse field. This is not integrable. Not only not solvable, but not integrable. It has quantum critical point that we know from quantum Monte Carlo very precisely. So it's paramagnetic when its transverse field is strong, and ferromagnetic then when transverse field is weaker than this critical value. And we consider a linear ramp or linear quench where G was going from this initial number to 0, and ferromagnetic coupling was at the same time linearly increased from 0 to 2. And midway during the ramp, the system was crossing this quantum critical point, quantum Kibble-Zurek mechanism. Actually, it's Żurek. The quantum Kibble-Zurek mechanism predicts this length scale and this time scale, as I said before, with this scaling hypothesis. And these are results of IPEP simulations. In addition to IPEPs, we had neural network simulations and MPS simulations for small systems. So here is the top panel is, I'm afraid the letters are small. Horizontal line is a scale distance. This is two-point correlation function, two-point ferromagnetic correlation function when the system is crossing the critical point. So here is a scaled distance, r divided by psi hat by the Kibble-Zurek length, and here is a scaled correlation function. And different colors mean different quench times or different times. And as you can see, or in fact you cannot see, but you must believe me that always different colors are single plot. And the single plot is the scale function. I have to set the first argument is 0 because this is correlation. It's a non-universal function, but after proper rescaling, you just get one scaling function that doesn't. And the bottom panel is excitation in function of time. Time 0 is when we are crossing the critical point. Energy is multiplied by 2 power 3 in dimension. And different colors are different ramp types, and as you can see, for a stronger ramp, they collapse to the same plot. Mechanism in near of a critical point. Oh, sorry. This would be succeeded to simulate in the paper. Dynamics. So, in other words, the system gets excited by the Kibble-Zurek mechanism, enters the ferromagnetic phase, and its evolution is not trivial. There is some thermalization going on for the ferromagnetic phase with a state with a size of ferromagnetic domains. Typical size of the domains is set, and with time, these domains are ordering. There is state ordering going. Lot of produced inside the system. This is why tensor network stations fail eventually. And this problem was simulate quantum state with Rydberg atoms. So I made a paper by looking at data ordering kinetics. They have shown that the size of the domain goes like square root time. It sounds like what has been measured are transverse oscillations of the transverse magnetism, but also satisfy a scaling. It's to measure transverse magnetization, either in Rydberg atoms or in D wave. Okay, so that preparation for that D wave paper, a long list of collaborators who are responsible for the hardware. And there are some theoreticians here and there who parasite the work. Transverse magnetic field. It's a ramp down to 0. We start from a non-zero transverse field. All spins are polarized along X. This is paramagnetic phase. So the transverse field is ramped to 0. And at the same time, the Ising coupling, J, is ramped up. And in general, this target Hamiltonian, this is quantum annealing. In the language of quantum annealing, this is target Hamiltonian. We have Ising couplings between different spins, not necessarily nearest neighbors, but here I will focus on random couplings between nearest neighbors. Yeah, so it's a random Ising model. So this is a ramp from a paramagnetic phase to a spin glass phase. The advantage of the spin glass phase is that there is no post-critical dynamics. So there is a Kibble-Zurek mechanism, excitation near the critical points, and then these excitations are localized. They do not spread entanglement over the system. If there is thermalization, it's very slow. And different lattices were considered: square lattice, cubic lattice. That's what we did with tensor networks. But in quantum annealer also considered diamond lattice, big leak lattice with high connectivity, just to make it hard for any classical methods. And on the classical side, matrix product states were used, PEPs, and neural quantum states. Matrix product states are, well, I didn't introduce them. They are a sort of quasi one-dimensional tensor networks, but you can use it in 2D. But in order to use it in 2D, you have to snake this one-dimensional tensor network over the lattice. And the consequence of this is that bond dimension has to grow exponentially with system size. So this is a very, very stable method. DMRG and all these tangent space methods can be used, but it's limited to small system sizes. Nevertheless, in small system sizes, it's used to obtain the ground truth. And with this ground truth, one can estimate quantum processor errors. And in our work, we are looking at the errors of sigma z correlators. So this is how correlation error is defined. Here, C wave is the ground truth correlation, and all correlations are included here, not only nearest neighbors. We also consider Binder cumulants and sometimes for small system full probability distribution. So let me first mention neural quantum state. That's an artist's idea of a neural quantum state. I don't want to go into details because I'm not an expert, but what is important, there is a very high connectivity between different neurons, quantum neurons. And that's why it is expected that this ansatz can accommodate a lot of entanglement. So in this sense, representability of a quantum state should not be a problem. To make a long story short, neural networks in this problem have a sampling problem. Here is autocorrelation time. It's a Monte Carlo method. You have to do sampling. And when you are doing Monte Carlo sampling, there is autocorrelation between different samples. And here is this plot shows how autocorrelation time depends on time during the run. So at first it's very small, but after you cross the quantum phase transition, it suddenly increases by orders of magnitude. And it quickly becomes very inefficient. So as a result, neural quantum states were limited to small size and small anneal times. Okay, so then we came as, say, experts on kind of experts on PEPs. And we did simulations with PEPs on finite lattices, 8x8 cylinder, for instance, with cylinders. So there were periodic boundary conditions to make it harder for us. I told you before about this truncation error. So truncation error for a single gate is a Frobenius norm between the target diagram on the left and the variational diagram on the right. And when we make a time evolution, many trotter gates, then we can define accumulated truncation error. It's a sum of all trotter errors on a given board. So, well, it's a relevant measure of error if you assume that that errors add up, that they are additive. Yeah. And then we made experiments between correlation error and this truncation error. And here is a correlation error. And here is a truncation error, and as you can see, there is a strong correlation. It turns out that the correlation error is roughly 1/10 of this accumulated truncation error. So it turns out that this accumulated truncation error is very relevant. So in fact, we can evaluate our PEPS simulations even when we don't have the ground truth from the matrix product state. And okay, it was a hard work. We tried different truncation clusters. So here is the simplest. We apply a gate to these two sides, but we include only nearest neighbor sites into this cluster to do this optimization with a non-trivial metric tensor. We considered also bigger clusters. These 4 methods can be contracted exactly. So when we know that the metric tensor is, after exact contraction, we know that it's not only Hermitian, but it's also non-negative. So we don't have numerical instabilities. But if you want bigger cluster, then you have to calculate a boundary MPS. And with this boundary MPS, you often end up with a metric tensor. You have to make approximations. You make truncations, basically, again. And then you often end up with a metric tensor that is not non-negative. And we also tried other ideas. For instance, PEPS, plaquette PEPS, where single tensor was covering a plaquette of 4 spins instead of just 1 spin, just in order to make it. The idea was to make a better use of a bond dimension. But the problem is that the bigger is the cluster, the more computationally expensive is the method. And the computation time also increases with the bond dimension. Here we plot the truncation error in function of the computation time. That depends both on bond dimension and the cluster size. Different symbols correspond to different cluster types here. And we compare them for different annealing times. Here, this ramp is done on a time scale of annealing time. For 2 nanoseconds, we have no problem. We can, first of all, the horizontal line is the error, estimated error of a quantum annealer. So for 2 nanoseconds, we have no problem. We can provide much better results than quantum annealer. It's still true for 4 nanoseconds. For some of the methods, it's also true for 7 nanoseconds. For 10 nanoseconds, yes, it's still possible with the best method, but we fail for 20 nanoseconds. Again, the same plot, but this time we choose the best method here. And we plot it in function of PEPS bond dimension. Again, 2 nanoseconds, okay, we can do much better than a quantum processor. For 7 nanoseconds, we become much better for large enough bond dimension. But for 20 nanoseconds, it's too hard. Yeah? So this, but I must say, so this sort of, but we have no problem with system size. So PEPS has no problems with system size. So we fail. Basically, this is a quantum advantage. Okay, this work was done a year ago. Nowadays, we can do 20 nanoseconds. We still need to write a paper. We have improved the methods. We can probably do 30 nanoseconds, but we cannot do 40 nanoseconds. So this quantum advantage is still there, but they have to make more effort to show. They would have to make more effort to show, to reach the advantage over PEPS.
May I ask a question?
Yes, please.
Could you comment on the geometry? Why is it cylinder? Is it dictated by the quantum processor?
No, it was made cylinder to make it hard for us.
Ah.
make it hard for tensor networks. Yeah,
Understood.
no, it was a very strange collaboration because we met every week, and whenever we came with some progress, whenever we brought some progress, we had some small success, they were not happy. That's not what you expect from your collaborators. Yeah, so it was deliberately made this way to make it harder for any classical method. Yeah, so but we didn't.
Can I ask one more question? Excuse me.
Yes, please.
This is 2D, 3D spin glasses. My impression is that you have again about about the dynamics near in the neighborhood of the phase transition. But what is a critical point? To my knowledge, this is not known. What is happening with say 3D spin glass, especially nearest neighbors?
Right. Okay, so I don't know where it's known from, but it seems to be known. I would have to search literature where they know it from, but probably
it might be, but
yes, but
okay, maybe I missed, but my impression.
Yes.
Okay. No.
Yes, you are probably right. It may be that here, for instance, we can see that we are crossing critical
No,
point.
but anyway, known or
Yes.
not, you are trying to work in this certain small neighborhood of the critical point. What is the point around which you work?
No, not really.
So
We make
something.
We make a full ramp. Full ramp is made both experimentally by quantum annealer and in our simulations. So
you don't care about whether there is a critical point. You're just trying to follow to construct numerically the dynamics.
Dynamics, to simulate the dynamics. So I don't care where precisely the critical point is, as long as there is a critical point.
I see. Okay. Thanks.
Okay, so we also attempted 3D simulations, but for 3D simulations was even harder. So simulation time was limited to 4 nanoseconds. But I think a real bottleneck at the time was calculation of expectation values, or at least that's what we thought until right at this time. An excellent paper was posted on arXiv, and it came from Kharkiv. And but still, yeah. So from that paper, we learned how to calculate expectation values in 3D, but still our annealing times that we could reach were very short. 4 nanoseconds was a maximal. So now I'm trying to do. Well, I'm running simulation, Monte Carlo calculation of expectation values in 3D. In some situations, it may be more efficient. We didn't try it with more complicated lattices. Okay, so that's a quantum advantage. Here is another experiment. Also kind of, this one is by Google, analog digital quantum simulator. And again, a similar problem, Kibble-Zurek-like problem, even though the focus of this paper is not Kibble-Zurek at all. They are aware of it, but they are more interested in thermalization after the critical point. So this is their Hamiltonian. The digital part of a simulator, this is the Google machine. Yeah. So it's usually used, it's known for its digital calculations, but here they used the digital part just to prepare the initial state in some situations. But then they do analog calculation, that's how I call it, but that's actually say quantum annealing or a ramp across a quantum critical point. They start from this Hamiltonian, and they end in this XX model. Here is the ramp. The black line is the transverse field, and this orange line is this antiferromagnetic coupling. There is a critical point where U1 symmetry is broken. It's a 2D model. Its location is known approximately, but it's there, and its universality class is known. So we know how KZ correlation length should scale. It should scale like a ramp time to power 0.40. This is 3DXX universality class, like helium-4. Now, this is not the main subject of their paper. On passing, they show that near the quantum critical point, the correlation length in the system scales like a ramp time to power that is close to 0.4 within a reasonable error bar. So it looks like KZ prediction. Okay. And then, okay, we saw this paper. We cannot simulate thermalization, that is their main subject, but we can simulate KZ near the critical point. We can simulate the excitation of a system near the critical point, but we are not able to follow thermalization after the critical point was crossed. So we calculated, we did simulation with IPEPs on infinite lattice, and here is a correlation length at the critical point. We get this Kibble-Zurek exponent, and we get this exponent for this relatively fast ramp times, the same ramp times as in this experiment. Here is a collapse of a correlation function again. So this is infinite lattice. These simulations demonstrate that for this ramp times, on infinite lattice or large enough, big enough lattice, you can get the KZ exponent. These ramp times are slow enough to go into this universal regime where you get this exponent. But we also did 8x8 lattice, 8x8. This was done by matrix product states, 8x8, because that's the size of their system. And here we plot correlation length at the critical point in function of the ramp time. As here is the predicted slope. It's a log-log plot. The predicted slope 0.4 is here, but this is what we get from simulations. It's twice the KZ slope, and then there is a saturation. So this looks like, okay, a much steeper power law, and then a crossover to adiabaticity. Adiabaticity, because it's a finite system, so, well, there is no critical point. There is a finite gap at the critical point. And we also look at excitation energy at the critical point, near the critical point, and it follows a power law -2 instead of -1.2. And this is characteristic power law when you make a critical ramp and then you stop a ramp in a system with a finite gap. You can get this -2 from adiabatic perturbation theory. You don't need to consider any critical phenomenon. Oh, it's 1 hour is gone. So there is a contradiction between quantum simulation and our numerical results, and we will discuss it on December the 8th when we have a seminar for Google. And we will see what happens. Okay, so I was talking about time evolution most of the time. So let me go back to the thermal states. This is what I like the best, because that's most promising. In time evolution, where this entanglement is so large, we must fail in comparison with quantum simulators. So we can only serve as a benchmark, yeah, to show that, okay, that they are eventually better than us. So what we actually do, we use a purification. So every lattice site For every physical lattice site, we introduce an ancilla partner. And then this mixed thermal state is represented as a trace over ancillas, over this unphysical ancillas. It's a trick to work with a pure state instead of a mixed state. And then we make evolution of this purification, starting from purification at infinite temperature, where we can choose this purification to be a product state. Zero bond, well, bond dimension 1, no entanglement. And there are some technicalities. I will not go into this. I just want to say that to make progress in these simulations, for every new model, you have to make a breakthrough on the algorithmic side. It's not just an application of a black box. Fermi-Hubbard model, 2D, the Fermi-Hubbard model. Monte Carlo sign problem, strong, especially for strong correlations. And here we consider the optimal doping, optimal for high temperature superconductivity, but not optimal for any classical simulations, as we know. It's a 40 years old story. We use U1 symmetry to make our tensors more compact. Checkerboard ansatz. It was a record bond dimension of 29, and we reached temperatures down to 0.16 at that time. And we work with infinite system. That's a main advantage of our method over other methods. I will not go into results. For example, I cannot go much into results. Specific heat, there is one peak. Here is half filling, one fermion per site. High temperature peak where double occupancy is suppressed, medium temperature peak where anti-ferromagnetic correlations begin to build up. This is half filling. And this is this optimal doping. We have a high temperature peak where double occupancy is suppressed, but this anti-ferromagnetic peak is washed out, almost washed out. Yeah, and this is due to holes. When you inject a hole into anti-ferromagnetic background, it can hop, or fermions actually, or electrons can hop the other way, and this hole leaves behind a string of ferromagnetic bonds. So it destroys the anti-ferromagnetic order, and this results in entanglement, and there are some simple theories that are called string theory, because it's like a string. So here we calculated all sorts of long-range correlators, anti-ferromagnetic correlators, short-range anti-ferromagnetic correlators. Let me stress, no finite size effects. It was all converged, and there were no finite size effects. I'm stressing this because at that time, we could compare only with DMRG on a 6x6 lattice that obviously has strong finite size effects, and with that experiments of 2018 with 25 atoms in a very non-uniform trap. All these plots look very similar, but we are the only ones that work in thermodynamic limit without finite size effects and without imperfections of a Hamiltonian. Okay, then the second work is on the TJ model. That's a strong coupling limit of a Hubbard model. We switched to the TJ model because it has less entanglement, because short-range super exchange entanglement due to super exchange fluctuations the short-range entanglement is eliminated by the Schrieffer-Wolff transformation. And when you obtain this model without double occupancy, you have only 3 states per site instead of 4, so there is less room for entanglement. And in this model, we can, and with some improvements in algorithms as well, we can go down to temperature 0.1. And we stop at 0.1 not because it fails at 0.1, but because we are using the checkerboard ansatz, and the checkerboard ansatz is not flexible enough to accommodate the stripes, charge density wave. And this is what is expected at lower temperatures. So we have, so we stopped here just in case. And now we have an ongoing project on stripes. We're pushing this temperature, we're pushing to lower temperatures with a more general ansatz. But in order to make progress, that's a very technical digression for experts. In corner transfer matrix renormalization group, we took care of multiplets. Well, I don't know whether it's known to other practitioners or not, but at least we realized that if we want to make CTMRG quickly convergent, you have to look at the spectrum of a corner matrix, and there turn out to be multiplets, and you shouldn't stick to a predefined bond dimension, environmental bond dimension chi, but you should adjust this bond dimension to accommodate full multiplets. You shouldn't cut these multiplets. This makes convergence much faster, and expectation values are much more stable. So again, some results like specific heat, spin susceptibility, charge compressibility, D-wave correlator. We didn't find superconductivity here at finite temperature. There are some controversies if there is superconductivity in a TJ model. It was for a long time it was assumed it's known without next near, there is no superconductivity without next nearest neighbor hopping. Now there are some claims that even without next nearest neighbor hopping you can get it, but we definitely cannot see long range D-wave correlations at these temperatures. What we liked most were some 4-point, 3-point correlators. So here is an example. Okay, here is a definition. We calculate 3-point correlator. This H is a projection operator on a state with a hole. And then we have two spin operators at nearest neighbor sites. So this is a 3-point correlator, and now we can consider different 3-point correlators. You keep your hole here, but you consider, say, 2-point correlators here, or nearest neighbor 2-point correlator, or next nearest neighbor 2-point correlator, anywhere on the lattice. And this is a picture that you get. So at the central site, there is a hole. We know it's there because we placed this hole projection operator there. And at the different links, the links that are blue are more antiferromagnetic than in a reference state without a hole. And the red bonds, nearest neighbor or next nearest neighbor bonds, are more ferromagnetic than in this reference state without the hole. So it's kind of hole polaron effect. And the size of this polaron increases as we increase density of fermions from 0.85 to 0.9 to 0.95, because it increases simply because at half filling there are longer range correlations. But it also increases as we lower the temperature from 1/2, 1/6 to 1/10. And okay, we got interested in these correlators because this is what was meant in recent experiments. We are sort of going in parallel to experiments by Bloch group by Bloch and Greiner's group in Munich and MIT, Harvard, MIT. They are both, in fact, from Munich. And now they are working on stripes, and we are also working on stripes. So as far as thermal states are concerned, I would say there is no quantum advantage, right? Because we can make the simulations in parallel to experiments. But of course, I'm joking. There are things that we cannot quantum simulate. So okay, so well, I don't have a short message, just finite highlights. The main character is infinite PEPs. So I talk a lot about Kibble-Zurek mechanism and this kind of spectacular, very popular paper on computational supremacy by D-Wave. So they have demonstrated it, but this is a very, very special quantum computer. So the quantum supremacy was demonstrated for KZ in spin glasses. And I want to highlight our finite temperature simulations. And that's something we want to, that's our main research topic, while the time evolution simulations are there mainly to talk with experiments, comment on experiments, provide benchmarks, etc. We don't expect to be very successful for real-time evolution. There is too much entanglement. Okay, thank you for your attention.
Professor Dziarmaga, so thank you so much for your insightful talk. And now let us have discussion, comments, questions. Ilya Lukin, please.
Thank you for your wonderful talk. I have a couple of questions on the algorithm of neighborhood tensor update. So first of all, you use environment which includes two nearest loops for the bound. So, but the rest of the system is treated kind of trivially. Does it make sense to include some, for example, belief propagation based environments to?
Yes, it does. Definitely. So that's what we are doing now, because I told you that, okay, we can do 20 nanoseconds. Actually, our science paper was challenged by people doing belief propagation. And they did 20 nanoseconds just by belief propagation. Well, it's sort of complicated story. We are trying to make sense out of it. I'm afraid I must oversimplify it, but it turns out that with belief propagation, with say Joseph Tyndall, for instance, and cells, and who else was involved? People from Flatiron Institute. So they challenged our work with belief propagation simulation, and they succeeded in simulation of 20 nanoseconds. Right? And then we learned belief propagation and included belief propagation into this neighborhood tensor update. So for instance, when we do a cluster like this, we attach this belief propagation tensors. I don't remember their name, but we attach them at the boundary of this neighborhood cluster, and this makes simulation more stable. And even for the spin glasses, we can get better results than people from Flatiron Institute. So we are now trying to make a paper about this. And the reason why they succeeded with spin glasses in this case is that the loop correlations in the system are very weak. So you can do belief propagation like in many previous quantum supremacy claims where they succeeded because there was no loop entanglement. And apparently here the loop entanglement is also very weak. But we also applied their belief propagation to this model, to the pure Ising model. Yeah, and this kind of standard condensed matter setup, and it failed miserably. So it's no good because here we have strong loop entanglement. So I recently made a paper on some loop truncation. I'm not quite happy with technicalities of this paper, but there is some discussion there, not about belief propagation, but how to truncate, how to make truncations in loopy tensor networks. Does this answer your question?
Yes, thank you for your answer. Just a small question, additional question about similar topic. So you have described how this algorithm may be applied to thermal states and to time evolution. So what about the ground states? Does it work better than simple update without further modifications?
For the ground state?
Yes.
No, it's no good. It's no good. I mean, you probably mean imaginary time evolution to the ground
Yes.
state. Well, I noticed that you were doing something like that in 3D, right? Am I correct?
Yes, we are doing this, but with simple update at the moment.
With a simple update. So yeah, in 2D, it's well known that any imaginary time evolution is worse than variational methods. In 3D, you probably know more than me. But I think, okay, we try to do this real-time evolution in 3D. I didn't include it here. But there it's very expensive to make these clusters. So you may gain something by making a non-trivial cluster. And in fact, the clusters we had to cut the loops in the clusters. So actually, including loopy clusters is too expensive. But then I'm wondering if you do singular value decomposition, this is well, I don't know. I have to make a closer look at your results. So we tried and we failed. In the end, we used clusters, sort of big clusters, but actually the loops were cut. So you could probably also do belief propagation there, or you could. Yeah, it was. Yeah, so I think you could use a non-loopy clusters. They are described in the supplementary material to this science paper, but well, it's nothing extraordinary. You can figure out how to do it, and there is some advantage, but at this stage it's not published work. I would say that attaching some belief propagation tensors there makes it much more stable. Somehow, because as you said, I include something into this neighborhood, but the rest is left. I just forget about it. It's good to include the rest of the lattice, at least as this belief propagation tensors, just to attach them here instead of leaving these bonds. So that's a sort of thing that we are doing here. We include this side, but we contract these bonds that are not directly attached to this neighborhood. Instead of this, you can use a belief propagation tensor here. So in 2D, in some situations, this makes it much more stable, and you can go beyond singular value decomposition, I think. But you know, sometimes it helps, and sometimes it doesn't help. We don't know what's the rule.
Thank you. And a final brief question. You mentioned that you treated three-dimensional system with Monte Carlo sampling. So is it like chain Monte Carlo or like sampling from PEP's methods, which are also developed?
Yeah, it's sampling from PEPs. So it's like, you know, you are working with a a single layer perhaps. That's the advantage, huge advantage. And I have a box, say 10 by 10 by 10 box. So I start from top and from the bottom and make some boundaries as you did in your 3D, but you did it for a double layer perhaps. And then I have a bottom boundary and top boundary, and I include, it was running for 2 months, so I include one layer in between. And then I make a sort of 2D matrix product state with some, we call it a zipper method, but it's basically a one-dimensional boundary. And I update tensors. Yeah, so it's more efficient because it's a single layer, but then you have to do a lot of sampling. So I don't know what is better. Allo is better, or your exact or semi-exact methods are better. For me, it takes sampling takes a lot of time because I applied it to this simulations where I calculate excitation energy, and excitation energy is a difference for slow ramp times, is a difference between two energies. They are very close, so I have to do a lot of sampling to get this number with small relative error. Okay.
Thank you for your answers.
Jacek, let me ask you about, I see two more questions, so I will be brief. About Kibble-Zurich mechanism and the related adiabatic impulse model. You said that it is natural to simulate this with D-wave quantum coherent annealers. And you've mentioned also that this is simulated with the Google computers. Can you compare and comment on this more? Why two different quantum computers both are efficient, and why gate-based computers are also good for Kibble-Zurich mechanisms and the related systems?
So it's a gate-based computer indeed, or I should put it differently. It's a hardware. It's a machine that is normally used as a gate-based computer. But this time, they made an exception. And they use it just to make evolution with a Hamiltonian, with a time-dependent Hamiltonian. So this time, it's the same hardware that we have seen in all the media, all the newspapers, but it's used for evolution with a Hamiltonian. So in this work, actually, it's not a digital simulation of a ramp. It's an analog simulation. It's done in the same way as in D-Wave. With gates, people tried with gates, and they succeeded in getting something, but you know how it is. Let's say 2 years ago, you could do something with a digital quantum computer, get something with say 20% error and publish it in a good journal. But it was not something useful to physics, really. But those kind of hype.
Yeah, thank you. Gleb Skarabagata, please, but please be concise.
Okay, just to understand better, if you apply your algorithm in reverse order, what happens? I mean that what happens with time reversal symmetry in this in all this story?
You mean the KZ-like story, or?
I mean that the truncations are involved, like generalized projection measurements, and this should spoil time reversal symmetry of quantum evolution. That's why if you apply, in principle, any kind of such algorithm in reversal order, then probably something should change in the observables you calculate. It's like sort of hysteresis, hysteretic behavior.
Yeah, you mean that you want me to make evolution one way and then reverse evolution?
Yeah. I mean your quenches. For example, is there a difference in which time direction you make your quenches? Because you quench two parameters simultaneously, and in principle, it's possible to do the same in opposite time direction. It's interesting whether will be something different or not in such a case.
Okay, so I can reverse the KZ quench, yes, or ramp actually. Quench is misnomer. It's there because it started in classical phase transition where they were trying to make a quench in helium-4 bucket, but actually it was a ramp so for instance in say quantum Ising chain, when we start from a paramagnet and we end in a ferromagnet, this is what we get. The excitations are kinks. But if I understand your question correctly, or your idea correctly, we could start from a ferromagnetic ground state and drive it to a paramagnetic phase. And then you also get excited state. This length scale is also relevant, but the excitations are in paramagnetic phase. All spins are in the ground state are polarized along X, say this way. So then the excitations are reverse spins in X, and their density is set by this length. I don't know if this is what you were asking.
No, probably no. I'm asking whether so there are certain parallels between real-time evolution and imaginary time evolution. So my question is whether truncation procedures add something irreversible to the system.
Yes, they do. Yeah, okay, truncation procedure depends on truncation error, of course. If it's negligible, then in principle they should add nothing, and then you could reverse this dynamics, right? But if you have truncation errors, with truncation errors, you could, for instance, follow the ground state in adiabatic evolution. But if you make truncation errors when you are exciting the system, it's heating up as a result of truncation errors. So yes, definitely they do. In this sense, they break time reversal.
So am I correctly understand that the more you truncate your system, the more you heat it?
Yes, or it depends on the setup. I mean, if you simulate adiabatic evolution, right, and you make these truncations, when you are heating the system, you can even make an experiment where you obtain the ground state, say a non-trivial ground state, by the best variational methods with automatic differentiation and so on, with that they provide ground state energies with similar precision to quantum Monte Carlo. Okay, so this is the initial state represented by PEPs. And then you run a time evolution. Now, because it's a Suzuki-Trotter decomposition, this evolution if you make a full step, then you should full time step, you should return to this original ground state. But there are these gates in between. Yeah, so there is a non-trivial evolution after you apply where is it? You apply this Trotter. You apply this Trotter gate. Yeah, so the state goes away from the ground state. Then you apply next gate, it makes another move. Then in principle, after the third gate, it should go back to the ground state if the time step is short enough. But you make truncations on the way because it's a non-trivial evolution. So this ground state may heat up after sufficiently long time evolution, even though in principle on paper you are doing nothing. You have a ground state and you are simulating time evolution with the same Hamiltonian. So yes, this is what happens.
But then, if such happens, then probably it's hard to reverse all this procedure in backward direction.
Yeah, so I would say, as I said, real time evolution is hard, and doing it in reverse is even harder.
Maybe with this, I would like to ask Andrei Sotnikov about last, probably short question.
Thank you for a wonderful talk. So my question will be then rather general. So with these quite advanced theoretical techniques that you showed us, do we still need the quantum computer? What is your opinion on that?
That was a kind of question I was going to ask at the beginning. Or but that's what I was suggesting with this, say, Hubbard model. And here we go, just step in step with experiment. The only reason why we are slower is that we don't have enough students. And yeah, it's a very good question. Yeah. Because in principle, okay, we get all these correlators. Probably there are some quantities that are not easy to calculate with PEPs or with tensor network. But I would say that whenever we can get results, they are more precise than what we can get from this quantum simulator. But okay, but I think this is not their last word, what they are doing with the Hubbard model, right? They are very smart people. They may invent how to do next nearest neighbor interactions and add more things that will introduce more entanglement and so on. And that's one reason why it's worth making these quantum simulations. And another reason, it's more speculative reason. In principle, you can. Okay, here we are looking, say, for a ground state, or with most successful people who are like Philippe Corbeau and so on. They get ground states with very Hashik. They get it very high precision, right? But for instance, if you want to do, say, topological quantum computation, then preparation of a ground state is just the first part of the story. And then you want to make some time evolution to do the computation. And that's something that I think we cannot do. And they can. So yeah, so I wish them good luck. But for the time being, it's fun to compete for a while. Whereas there was my grandfather told me a story. It's a local legend. A railway was built in 1905 in the neighborhood of his village. He wasn't born yet at that time, but the legend was known for a long time. So a railway was built, and there was a farmer who was very proud of his horses. Yeah, and he was drinking too much, and he made a bet that he can start together with a train and reach the next county town 13 kilometers away faster than the train with his horses. Yeah, so they made a bet, and then the race started, and he won. Yeah, his horses died. He won. Yeah, so in a short term, he was successful, or sort of parallel to the train. But in a long term, we know what happened. So I hope at least that our simulations can help to make quantum simulators better. That's a long term. I hope we are bound to fail. Yeah, I wish they were successful. For instance, we sort of tried to criticize this Google experiment. We are going to have a discussion with them. So I hope it's a fruitful discussion. There was a long time ago when we criticized D-Wave. There was a paper, Defects in Quantum Computers. We tried to get KZ and we didn't get KZ. They got angry. Their lawyer called us to ask what we are going to do with our work, and we said, okay, we just want to publish a scientific paper. Okay, no problem. But they repeated our experiment on D-Wave, and they learned something, and I hope it was a motivation to make things better. They realized that something is wrong. So yeah, I think it's mutually inspiring. Yeah, but it's a good question. It's a very provoking question.
Thanks a lot. You provoked this provoking question.
Exactly. Yeah. Thank you.
Very nice discussion, very beautiful talks. Thanks a lot. Good luck in your further research, and thanks a lot for being our speaker today.
Thank you.
Dear colleagues, thanks a lot for participating in our seminar. See you next time.
Bye-bye.
All the best. Bye-bye.
Goodbye.
Thank you.